皆さんおはようございます。北大のパウエル・コートニーと申します。すみませんが、今日は英語で発表します。どうぞよろしくお願いします。So my presentation is entitled Cloud Resource Allocation Optimization by Equivalent Transformation and Evolutionary Computation and Integration with Infrastructure Middleware. So our objective is simply to generate optimal resource configurations from various choices provided by cloud providers based on the requirements and objectives of users. And this is mainly for scientific workflows. So we actually developed and implemented an optimization engine that solves constrained many objective problems for resource optimization in intercloud environment. And some of the issues we considered were cost and make-span minimization, workflow availability and resource reliability maximization, independent and simultaneous workflow scheduling, and constraint satisfaction. So at the bottom of the slide, you can see the conceptual diagram where we have our user sending specifications and requirements to the resource scheduler, which communicates with the many objective optimization engine. And the optimal deployment configurations are returned to the user. So why do we need such a mechanism? Well, users want to combine optimum services, machine types, etc. for their workflow. But today we have a wide variety of choices. For example, we have numerous providers such as AWS, Azure, GCP, IBM, etc. We have numerous machine types, and we can execute in many regions of the world. There are also numerous, well, not numerous, but quite a few purchase options. In addition to that, the users need to satisfy various constraints, and especially when dealing with genome data, there are numerous restrictions on the data storage location, where the data can be executed, etc. So we can see that users have different objectives and requirements that must be satisfied. So here's a layout of our actual framework. We call it the multi-objective optimization predicate logic defined specification framework. And in this system, we see where we get our system requirements. And these are described in the PLS formula, which is first order predicate logic. And from this formula, we generate a set of definite clauses representing the constraints. And we use equivalent transformation to generate feasible configurations from those constraints and requirements. And from those feasible configurations, we select the optimal and feasible cloud resource configurations. So what exactly is PLS? PLS, as I said before, is a predicate logic defined specification. It's actually a unique formula for specifying system requirements, and it's based on first order predicate logic. Here we have an actual formula where E represents the atomic formula and V is a variable that actually appears in the atom. And PLS is very easy to create by simply adding atoms that are required to represent the system requirements. For example, at the bottom, you see where we have a PLS and its components. So here we have financial budget, and we have deployment location, and we have the type of workflow or type of application. And we can easily add other applications or constraints by just creating a corresponding atom for those conditions. Now, equivalent transformation is actually performed by the iterative replacement of clause sets based on declarative semantic equivalence. And this is carried out by what we call equivalent transformation rules. And in this system, we have a query being described by a definite clause. And the answer to that query can be a unit clause or a number of clauses. So for example, here we have an example where we give the query to find two lists, A and B, that can give one list comprising 1 and 2 when they are combined. And this is a query, the definite clause. So here we have our answers. So these are the actual unit clauses. So we have a null list representing A and B being 1, 2. Another answer is 1 being A and 2 being B, etc. So as we said, clause replacement is performed using ET rules. And given the query, ET rule is successively applied. And in the intermediate state, we have a mixture of definite clauses and unit clauses. And the actual answer comprises unit clauses only. So what is MOGA? MOGA is a multi-objective genetic algorithm, and it's population-based, and it can find the Pareto optimal solution set in a single run. Now, in our system, it's based on NSGA 2 and 3, and it generates the solutions considering the trade-off relationships between the objectives specified by the users. Now, we actually need two different algorithms because NSGA 2 is only effective for 2 or 3 objectives, while NSGA 3 is effective for 3 or more objectives. So NSGA 2 actually uses crowding distance to get diverse solutions, while NSGA 3 uses reference points to get diverse solutions. But they both use ranking to specify the best solutions. And here we have two-dimensional, two-objective representation, and we have 3-objective representation. So this is the Pareto surface, and this is the Pareto front. So this is the actual flow for generating feasible configurations, where we have our PLS in the form of constraints. And from those constraints, we create allocations or configurations. And within those configurations, we search for feasible configurations based on historical data for the tasks, etc. And from those feasible configurations, we use MOGA to find the optimal feasible configurations. So here's an example for a two-objective problem where we want to minimize execution time and usage costs. And this is the workflow. Here we have our PLS. And this is the budget. And this specifies the locations where the machines can be executed. So we actually replace the definite clauses to get our answers. And we get our Pareto front here. So from this front, we can choose a configuration depending on your preferences. For example, this configuration is actually quite fast. Execution time is quite fast, but its cost is very expensive. Whereas this one is not as expensive, but execution time is quite long. So we also considered two workflow scheduling approaches, specifically independent scheduling and simultaneous scheduling. And you know that in independent scheduling, the time may have to be pre-booked or reserved. Large workflows can result in long delays, etc. Whereas in simultaneous scheduling, workflows that are submitted at the same time can be processed together, and idle time and resources can be maximally exploited. And where we have limited amounts of high specification resources, then we can actually allocate those fairly to different work groups more easily. So this is the actual flow for independent scheduling. Here we have our queue. And from this queue, we actually choose one workflow. We find the optimal configurations. And you can see the actual configuration, optimal configurations here, and the configuration for that. So for example, we have our distributed feasible universe for the previous workflow. This is our Pareto optimal feasible solutions. And these are a few examples of the actual configurations and objective values. So here you can see where this one has the highest availability and reliability, but the cost is very high. Whereas this one has a very low cost, but the reliability and availability are not as good. So the user would have to choose from among these configurations, depending on which objective they actually prefer. Now for simultaneous resource selection, we have all the workflows being processed together. So we cluster them by levels, and we combine the feasible configurations and the objectives. We process them together and obtain our Pareto optimal feasible solutions. Then we generate our workflows, objectives, and configurations separately. So the many objective engine developed was implemented as a application scheduler core in the implemented system. So here we have our system being implemented here. And the overall system was developed by, this part of the system was developed by NII Group, as stated before, and here NIG Group. So the AS core was actually implemented as a command line application. We have workflow input parameters and constraints being obtained by standard input. So here we have the time limit, the cost limit, etc. And it's executed in the system as an external program. Thank you. これで以上です。
ありがとうございます。ご質問を皆さん Q&A の方に書き込んでいただきたいんですが、まだ今のところちょっとないようですね。すいません、今後の発表の中でもですね、どんどん発表中に書いていただいて結構ですので、皆様よろしくお願いいたします。 それではですね、今のご質問に対して私からちょっと質問させていただきたいんですけども、ですね、これ今、最適な資源を求めるときにですね、よく時間がかかったりとかするんですけども、その元々のなんていうんですかね、項目、すみません、日本語で質問してよろしいですかね。
簡単に日本語大丈夫かな。
ですね、こういう要件って言いますか、それと、それが最適なリソースを計算するまでの時間の関係ですね。要件の数と、さっきの E ですかね。E とか V とか、その辺のところの数と、計算時間っていうのは何かこう、比例関係にあったりとか、そういう関係はあるんでしょ
計算、こういう PS フォーミュラですか？
はい。
計算、
エンバイロメントが今 ABC あって、これレベルがどう読んだらいいのかな。バジェットとか、エンバイロメントとかバジェットとかロケーションとか、いくつもの要素があると思うんですけども、それの数と、例えば、最適な、最適な資源を求めるための計算時間ですね。この要素の数と計算時間の関係みたいなのは何かありますでしょうか？
計算時間も、エクセキューションタイムですね。
そうですね。はい。
メイクスパンですね。そうですね。それも入れるですね。入れる。これはバジェットですね。ロケーションとタイムも、
そうですね。それはアプリケーションの計算時間のことをおっしゃってるんだと思うんですけども、そうではなくて、これ自体、この PLS フォーミュラを、実行して最適な、資源を求めるのにどれぐらい時間がかかるかという質問なんですけども。
そうですね。今、それはないんですが、小樽の初代の三浦先生が
そうですね。
それを探していたんだけど、それ、僕はちょっと、今、その情報は今ないですね。
わかりました。すいません、そうでしたね。ちょっと私も全体として質問してしまいました。申し訳ありません。
すみませんでした。
いえいえ。はい。はい。それではちょうど時間になったようです。ご発表ありがとうございました。ちょっと他に質問がないようなので、次のご発表に移らさせていただきたいと思います。パウエル先生、ありがとうございました。
はい、ありがとうございました。